In this video, we're going to cover section 5.4. Section 5.4 is the fundamental theorem of calculus. And the fundamental theorem of calculus, well, why did they name it the fundamental theorem of calculus? Well, they named it the fundamental theorem of calculus because it is the theorem that links what we've learned about derivatives, differential calculus, to integrals, what we've learned about integral calculus. This is the theorem that connects, provides us with an understanding of how there is a relationship between the derivative and the integral. Because while we know there is a foundational relationship in the sense that both of them are limits, it turns out that there's even a deeper relationship between the integral and the derivative, and the fundamental theorem of calculus brings that relationship to light. So before we can begin talking about the fundamental theorem of calculus, we have to talk about a type of function that we haven't seen prior to this moment. We've seen lots of functions. We've dealt with trig functions and exponential functions and logarithmic functions, polynomial functions, rational functions. We've seen a lot of types of functions, but this function that we're going to learn about right here is a new and different type of function. Now that doesn't mean it's a difficult function. It doesn't mean it's going to be more challenging than any other function we've encountered in the past. It just means it's going to be a different type of function. So what is this function that we are going to use to talk about the fundamental theorem of calculus? Well, we're gonna start. Let me get a different color here. We're going to take just the first quadrant. We can put the function anywhere we want, but we're going to put our function in the first quadrant. We're going to call this A. We're going to call this B. And we're going to draw a continuous function from A to B. Okay? So we have a function that's continuous. So this is going to be y equals, and we're going to call this f of t. All right? Y equals f of t. So our independent variable is t. Our dependent variable is y. So we have a function, and we are very accustomed at this point, having met the integral, to thinking about the area under this curve, right? What is the area under this curve? And we know how to write the area under this curve. The area, we know, is the integral from a to b of f of t dt. That's what we defined the area under a curve to be. We said the definite integral can be thought of as being the area. And if I integrate from a all the way to b, I get this entire area, and that's what we've done in section 5.1 and 5.2, and again in section 5.3. We've talked about this. But now we're going to introduce a new layer, an idea that goes along with this graph, where we know the total area is this. But the question then becomes, what happens? What happens if we draw a vertical line? We pick a point between A and B is what we've done. We've picked a point. And we ask ourselves, what does this equal? All right? We ask ourselves, what does this give me? What do I get if I only integrate from A to X? Now, if you're thinking what I'm going to get is the area between A and X under that curve, you're 100% correct. You're absolutely right. That's what the integral from A to X is. However, what if we allow X to be a variable between A and B? What if we allow x not to be a fixed point, but to be a variable point? What if we allow x to be any number between a and b? Well, if we do that, if we allow x to be any number between a and b, then this is going to be the area between a and x. But when x changes position, this is going to change value. So let's think about that again. X could be red, and it could be right here, and we would take this integral, and we're going to get a number. But what happens if x is here instead? Well, we're going to get a different value altogether. The integral from a to x is going to be this area right here, starting at a and ending at x. It's going to be a different number. It's going to change. So we're going to have a function, all right, that if we were back in an Algebra 1 class, we would say, well, you know, we would make a t-table. That's what we do. Well, what is this going to look like? What's our t-table from Algebra 1 going to look like? Well, our independent variable is going to be x, where a is less than or equal to x is less than or equal to b. So we're going to pick some x between a and b, just like we've done in the picture over here. What's our dependent variable then? Well, our dependent variable, right, our answer is going to be the integral from a to x of f of t dt. This is going to be our function. This is going to be our domain here. This is going to be our range over here. So if we look at this, the domain is just any x between a and b. You pick it, that's easy. The range is going to be the area from a to wherever you've given me the x. Now, what do we know about this? Well, we know the biggest it's going to be is the integral from a to b. The entire area is going to be the biggest y value we have. The smallest y value we have is 0. Because x, for our x, we could choose a, right? We could choose a as our x. And if we did that, then this would be the integral from a to our x, but our x would be a. So we would have the integral from a to a of f of t dt, which we know to be 0. But what happens if we pick x to be b, the other end? Well, then our y value would be the integral from a to b of f of t dt, which is going to equal the total area. Now, if we think this through, every x I pick is going to give me an area. Right? There is no x where the area is going to be undefined. I'm going to be able to find the area. The smallest area I'm going to get is 0. The largest area I'm going to get is the total area. And most importantly, I'm going to get all the numbers between whatever these two values happen to be. If I barely move x off of a, I'm going to get a tiny little area. It's going to be bigger than 0, but it's going to be small. If I move it a little bit more, the area is going to be a little bigger. So my y value, it's the area, is going to be a little bit bigger. And as I move x across, the area is going to grow. And it's going to grow without skipping any numbers. It's going to grow continuously. It's going to grow continuously. So we're going to introduce a function based on this picture. And our function is going to be this. We're going to say, well, this is actually a function. I'm going to call it g of x. We call this an area accumulating function. And as x moves, we accumulate more and more and more area. As x moves to the right, the area between a and x grows continuously. So, this is the function that we are going to talk about, right? And so g is the area under the curve between a, which is a fixed number, it never changes, our lower bound is always a, and x. This function is completely dependent upon x. So we call this the area accumulating function. Some books call it the area so far function. What's my area so far? Area here, then to here. For each x, what's my area so far? All right? So I'm going to erase this, and we're going to put an example and work with our area accumulating function and try to get this idea firmly into our understanding. And then, once we do that, we'll be able to move on. So we want to make sure, before we can talk about the fundamental theorem of calculus, since it is going to involve this type of a function, we want to make sure we understand this function. Okay? So let's just draw a function. We're going to make our function relatively boring. Okay? So here's 1, here's 2, here's 3, here's 4, here's 5. All right? So this is 1, this is 2, this is 3, this is 4, this is 5. And here's what our function is going to do. It's going to go up here to 1, 1. All right? And it's going to go straight across until we get to 2. All right? Then it's going to go up at another 45-degree angle until we get to 3. Then it's going to go straight across until we get to 4. And then it's going to shoot all the way back down to 0. All right? So this is our function f of t. This is our function f of t. In this problem, our a is 0 and our b is 5. Okay? And we want to have a conversation about this function right here, our area accumulating function. G of x is the integral from a to x of f of t dt. So what does this say? It says g accumulates the area starting here and we move to the right. X is our variable. So we're going to build our t-table over here. Just like we did back in Algebra 1. Okay? So we're going to start and we're going to say, okay, what happens if x is 0? Okay, so when we come over here, that's going to be g of 0, right? Let's go ahead and do this over here. That's going to be g of 0. Now, based on our function is right here, g of 0. Now, remember, our a is 0, right? So g of 0 is the integral from a, which is 0, to x is 0, of f of t dt. So this says g of 0 is the area under this curve between 0 and 0. And by our properties of integrals, we know that turns out to have no area, so that's going to be 0. Now, what is g of 1? Right? What's g of 1? Well, g of 1 is the integral from our a, which for our problem is 0. So that's the integral from 0 to 1 f of t dt. So that's the area under this curve between 0 and 1. G of 1 is the area of this triangle. Now we know the area of that triangle because I said that was going to go until it was 1 high. This right here is 2 high. So we know the area of this triangle based on what we learned in geometry, half a base times height. The base is 1, right? So we can write that out. It's half the base times the height. So we get G of 1 to be a half. So when we put a 1 here, we get a half. Do you see how we say we're accumulating the area? That's okay. We're going to do another example. What's G of 2? All right. What's G of 2? That's going to be the integral from 0 to 2 of f of t dt. So we want the integral from 0 to 2, not from 1 to 2, from 0 over to 2. That's the area under the curve from 0 over to 2. Well, we have the area of this, which we know is a half. We just found that. This is a square, so its area is 1. So G of 2 is going to be the area here, 1 half, plus the area here, accumulating the area. That's going to be 3 halves. What about G of 3? Well, hopefully you're beginning to see the idea here. For G of 3, we're going to have the integral, right, from 0 to 3 of f of t dt. Because our x is right here. Now what do? Well, we know that integral goes from 0 to 3, so that's a half, that's 1. We have to find this. Well, this has a square right here, yes, so that's a 1. Has a triangle right there, that's a half. So we have a half plus a 1 plus a 1 plus a half. This is going to equal 3. So when we plug in 3, out comes 3. We're accumulating the area. What about G of 4? G of 4 is going to be the integral from 0 to 4 of f of t dt. So that's going to include this rectangle. We go from 0 to 4. 0 to 4. That rectangle is 1 wide, 2 high, so that has an area of 2. So we have 2 plus 1 plus 1, that's 4, plus 1 more, we get 5. See, we're accumulating the area. So G of 4 is 5. What about G of 5? Yeah, I think you've got it at this point. That's the integral from 0 to 5 of f of t dt. And that's going to be, we're going to have to include the area of this triangle right here, aren't we? Now this triangle is 1 half wide. Sorry, it's 1 wide by 2 high times a half, right? So that's going to be 1. And we already know the area between 0 and 4 is 5, so we're going to add 1 more to that. We're going to get 6 here. So when we plug in a 5, out comes a 6. Now, all we found was G of 1, G of 2, G of 3, G of 4, G of 5. And we found our smallest area was 0, and our largest area, the area of the whole thing, we saw was 6. Now, could I have found a place where the area equals 4? Because we jumped from 3 to 5. But we only jumped from 3 to 5 because on our domain side, we didn't include everybody between 0 and 5. We just included 1, 2, 3, 4, 5. 5 distinct points. Is there a place where I could have gotten 4? I mean, could I have gotten 4 to show up if I wanted it to? And I think if you take a look at our picture, the answer is yes. This is a half, that's 1, that's 1, that's 1, that's 3, this is 2. If I would have only gone to 3.5, G of 3.5 would have equaled 4. I could have gotten there with G of 3.5. The integral from 0 to 3.5 of f of t dt. So, is there any numbers we would have missed, right? Are there any numbers we would have missed? If I pick now obviously I couldn't get to 7. Our total area only goes to 6. But could have I gotten to 3.9? Well, sure, I could have. I could find a place where I get to 3.9. So we could have gotten any number for our range, any number between 0 and 6. We could have gotten all of those numbers. There's a place on here where the area equals pi, because pi is between 0 and 6. I don't know specifically where it is, but it's there. Right? It's there. We could have found it. So this is the kind of function we're going to talk about. Okay? This is the kind of function we're going to talk about. And if f is continuous, right? If f is continuous like this, no holes, no jumps, no vertical asymptotes, then we're going to be able to say something pretty remarkable. And so it's time now that we've met the function, it's time for us to write down the fundamental theorem of calculus. So let's go ahead and get this out of the way. All nice and clean for the fundamental theorem of calculus. But, it's a big deal. We've worked hard to get here. So here we go. This is the fundamental theorem of calculus, part 1. And here's what it says. If f is continuous, no holes, no jumps, no vertical asymptotes. If f is continuous on a to b, then the function g, that's the same function we just met, the function g defined by g of x equals the integral from a to x of f of t dt, where x is between a and b, is, now here's the important part, is an antiderivative of f, that is, here it comes, g prime of x. If I take the derivative of this side, is going to equal f of x. For a is less than x is less than b. If we take the derivative of the right-hand side, the left-hand side, g prime, then when we take the derivative of the right-hand side, notice what happens, right? What is happening here? Well, we're starting here with g of x, and we're taking the derivative of that. Right? We're taking the derivative of that. Now, if we do that, we've got to take the derivative of the other side. Right? Because if I take the derivative of the left, I have to take the derivative of the right. And here's what the fundamental theorem of calculus says. It's a surprising result, but it's not a difficult result. It says if I take the derivative over here, we get g prime. We all know that. If I take the derivative of g, I get g prime. That's perfectly obvious. What's not obvious is what happens over here. If I take the derivative of an integral, right? Because that's what this is. It's the derivative of an integral. If I take the derivative of the integral, look what happened. The integral went away. The derivative of the integral caused the integral to disappear. The derivative of the integral caused the integral to disappear. Now that says something quite enlightening about derivatives and integrals. Because when you take the derivative of an integral, the integral disappears. So derivatives undo integrals. Now we know from our pre-calculus days what happens, what relationship we're talking about when we say, hey, one function, this function, when I applied it to another function, they undid one another. Right? This is what we said in pre-calc. And we said this happens when g of x is the inverse of f. That's what we said back in pre-calc. So what we're saying here is that derivatives and integrals are inverse functions of each other. Derivatives and integrals are related. They have this relationship. One is the inverse of the other. And inverse functions undo each other. So when I take the derivative of the integral goes away. All I get left is f of x. Notice there's no f of a, there's nothing. The derivative of this gives me just f of x. Now what does that mean mechanically, right? Mechanically, what does that mean to you and I? How does this work out? Well, let's just erase the bottom part, give ourselves some room down here, and let's write something down. We'll write down a problem, okay? A typical homework problem that we may encounter when we're doing problems in this section, okay? So here's an example of something that they could give us. They could say g of x is the integral from 0 to x of sine t squared plus 1 dt. Okay, they give us our area accumulating function. Now this one's more complicated than the one we did a second ago. We couldn't do the t table for this without a calculator, right? Because we would have to check and plug numbers in and find sine of that. That would take some work, but it's not the problem because that's not what we're going to do. We don't need to find g of 1, g of 2, g of 3. What we have to find is we have to find g prime of x. We don't have to find it twice. We have to find g prime of x. Okay. Now, the first thing we have to ask ourselves is this continuous? Well, it's a sine curve. Sine's continuous, but then to be continuous, of course, the inside function would also have to be continuous. T squared plus 1 is a polynomial, so that's continuous. So that function is continuous. So the fundamental theorem of calculus, right? We said f is continuous. We checked f. We saw it to be continuous, so the fundamental theorem of calculus applies. So it says if you want to find g prime of x, here's all you do. G prime of x is your function f with x stuck inside. You take your function, right here, sine. Sine's my function. Sine. And instead of t squared plus 1, it says don't find f of, your answer is not f of t, your answer is f of x. This value goes here. So this is the derivative. That's the derivative of that type of function. We needed it to be this kind of function so we could see how the derivative makes the integral disappear. Okay. That's all there is to it. I mean, that's it. That's the fundamental theorem of calculus. When I differentiate an integral, this bound, right, this bound, the upper bound, gets placed in here, and I rewrite it, and I'm done. Now, let's look at another example, because perhaps right now you're thinking it can't be that nice. Let's do another example. Let's say g of x equals the integral, right? And we'll say this goes from x to 4, and we'll just do it as the square root of t plus 1 dt, and they ask us to find g prime of x. Okay, they want us to find the derivative. Now, what are we going to have to do? Well, over here, we took the upper bound, we stuck it in, and we were done. I mean, that's what the fundamental theorem of calculus says. Take the upper bound, stick it here, and you're done. However, we've got to be a little bit more careful, more cautious with the problem we've been given. The fundamental theorem of calculus says the upper bound has to be my variable. The upper bound has to be my variable. Well, in our problem, the upper bound is not our variable. Our variable is the lower bound. Now, we know how to fix that. We have a property of integrals that says we can rewrite this by adding a negative sign, and we can flip the bounds. Right? That's the cost of flipping the bounds. So on some of the homework problems, when they ask you to use the fundamental theorem of calculus part 1, they may make the bounds upside down, and then you've got to put the x back on the top. But that's easy to do. We know if we flip the bounds, we have an integral property. This is we just put a minus out in front. Now it's set up. Now it looks just like the fundamental theorem of calculus. It doesn't matter what constant this is. So now we know g prime of x is equal to, we take this function and we plug in x. That's our derivative. But we have to not, we've got to remember not to lose our negative sign right there. So one of the things they could do to us in the homework, right? One of the things they could do to us in the homework to try to make the problems a bit stickier than this problem is they could provide us a question when the bounds are upside down. We handle that by reversing the bounds before we take the derivative, and then just don't lose your negative sign and you're done. Now, I know some of you are thinking it can't be that easy. There's got to be another catch. And I would love to tell you there is, but I guess it's not a catch. But it's not a big deal. There's another little bump that they could put into the road. Okay? And again, it's not anything we need to be overly concerned about. They could give us an example. Right? They could give us an example. That's written like this. G of x equals the integral. All right? And we'll make this a 2. It doesn't matter what constant that is. Now, we're not going to have to flip this one because the constant's on the bottom. But I'm going to put sine x right there. Now, that's not x. That's sine x. And then I'm going to have t squared plus 2 dt. Okay, so how is this problem different than the problems we've looked at in the past? Well, in our prior 2 examples, this was just x. It was x. Now it's a function of x. It's sine x. Now, what is that going to cause? Well, it's going to cause us to have to add a step. But it's not a surprising step. It's called the chain rule. We're going to have to do the chain rule. So g prime of x is going to equal, we're going to take the derivative of this. The integral is going to go away. Now we know how to do that. You put this in here. So I put it in there. So instead of x squared, since my function is sine, it's going to be sine squared x, right, because I have to square it, plus 2. I just insert it, nothing to panic about. But we're not done. We have to do the chain rule. We have to take the derivative of this. This is our inside. It's our inside function, and since it's not an x, we have to do the chain rule. The derivative of sine is cosine. And so we would have to multiply by cosine. Okay? So that's something else that they could do to us to cause us to maybe have a hiccup while we were solving some of our homework problems. They could, instead of making this an x, they could make it a function. Now what happens, and what I'm about to do right now is the worst case scenario. It's absolutely the worst case scenario. What happens if they give me a function, g of x equals, I integrate. Maybe I have right here the square root of t plus 4 dt. But my bounds are x squared and x to the 4th. Now, the fundamental theorem of calculus says I only work if my lower bound is a number. Our lower bound is not. It's a function. It's a function. See, that's not a number. I can't just put the x to the fourth in here and do the chain rule and be finished because I don't have a number here. But we have a property of integrals that says we can write this like this. Don't we have a property of integrals that says we can break an integral up into two pieces? We have that property that says we can break the integral from a to b up into an integral from a to c and then plus the integral from c to b. That's what I just did. Now, your question is, why did I choose 0? I can choose any number I want. You could choose 8. You could choose pi. You could choose 13. You could choose your lucky number 7. I chose 0. Now, before I can take the derivative, this one's already set up. Look at this side right here. This side is already in the perfect form for me to find the derivative. I got a number on the bottom, I got a function on top. Number on the bottom, function on top, ready to go. Over here, we're backwards. We're backwards. That's not a big deal. We know how to fix that. We know how to fix that. We're going to rewrite this. We're going to put a minus sign there. We're going to put the 0 down there, the x squared up there, right? That's what it costs us to flip our bounds. We've got to introduce a negative sign. We have the square root of t plus 4 here. Over here, we don't have to change anything, so we're just going to write this one like this. All right? And now we're ready to find g prime. Now we're set, right? We can find g prime now. Because both of our integrals are in the appropriate format. Number on the bottom, function on the top. Number on the bottom, function on the top. So now, it took a little bit of algebra involving our integral properties, but now we can find g prime of x. We know how to find g prime of x. We have a negative here, so that's minus. We write down our function. We put x squared inside. So it's right here for our t. We put our x squared in there, plus 4. Now we're not done. We have to multiply by the derivative of this. We got to do the chain rule. That's going to be 2x, right? 2x, derivative of x squared, derivative of this, 2x, plus, right? I'll write it down here because we're running out of room. Plus, here we're going to do the same thing. We don't have a minus sign, so we're going to have the square root. X to the 4th goes in place of my variable, plus 4. And once again, because that's not an x, I got to do the chain rule. So the derivative of x to the 4th is 4x cubed. And that's my answer. That's how we do these problems. So this is the fundamental theorem of calculus.